Hello Great Elves, welcome to the video on optimization part 1. So when you look at optimization, specifically it's referring to maximum and minimum word problems. So a lot of textbooks don't really use the word optimization just because it's a very fancy schmancy word. Most textbooks actually talk about maximum and minimum word problems. And you will see that's the way they describe it in the classroom mathematics textbook as well. So we might actually end up calling it maximum and minimum word problems rather than calling it optimization. Now, just very important, we're going to look at a couple of examples in today's video. I'm going to leave off the Luzandi method until tomorrow's video. So in tomorrow's video, I will go step by step by step. But today I need to do a couple of examples just so you can get used to the idea of doing these optimization problems. So to get a maximum or a minimum, and this is either, whether you're looking for the maximum or you're looking for the minimum, we always set the first derivative equal to 0. Now this follows straight from graphs. Whenever we wanted to find a turning point, and please remember turning points can be maximum turning points and turning points can be minimum turning points, we set the first derivative equal to 0. So if we want to get maximum or minimum area, or we want to get maximum or minimum volume, then you also have to go and set the first derivative equal to 0. So that, if nothing else, please people, remember this. Okay, so let's get started on the examples. These are all from the classroom maths book. I haven't included all the information, but I will just read from the textbook to give you an idea of what you are looking at. In example 1 on page 228, they say, a rectangular den for ostriches is enclosed using 400 meters of fencing and making use of an existing boundary wall. So they take an existing boundary wall and they take 400 meters of fencing and they just go and they take it in on these 3 sides. Obviously you don't need fencing because that's the existing boundary wall. So they just go and they put it on these 3 sides and it's the shape of a rectangle. Calculate the dimensions so that the area will be a maximum. So we want to go and we want to optimize or maximize area. So I'm just going to write it over there just so we can remember area is the goal. That is what we are trying to optimize. So if we are trying to optimize area, we need to first write down a formula for area. Now normally the formula for area is we're going to write area is length times breadth because it's a rectangle. But I don't really want to use length L and B. That's just awkward variables. So instead of using that, I'm actually going to go and I'm going to say, let's make the length equal to y and let's make the width equal to x, because that's the way they do it in the textbook. I would have rather made the length x and I would have made the width y, but let's stick to the way they do it in the textbook. So we're going to say, according to the textbook, let the width be x. We're going to say the width of the rectangle then there is x, and we're going to say let the length of the rectangle so there be equal to y. So the area of this rectangle is then very easy. It's equal to x times y. Now we then want to go and optimize area. And I stated up here, in order to maximize or minimize, in this case we want to get a maximum area, we need to set the first derivative equal to 0. Now whenever you do these problems, you're always going to notice after you've set up the formula of the dimension, or not, well, yeah, it is technically speaking the dimension. After you set up the formula which you want to maximize, then you have an issue. You have a little bit of a problem. And that problem appears right over there. Instead of having only one variable, we have 2 variables. Now, people, you cannot differentiate if you have 2 variables. You can differentiate if you have constants. So previously what we've done, like in the previous ones where we had those ax squared plus bx plus c, we said a, b, and c is not the independent variable. A, B, and C are constant values. So only x was a variable. But in this case, y is also a variable. They didn't tell me y is constant. Nowhere over here did they tell me y is a constant value. So I've got 2 variables. And that's why I first, before I can find the derivative and setting it equal to 0, I need to go and I need to substitute. So I need to substitute something to do with x in there. So that needs to be substituted with something to do with x. Now that is why we need to go back to this piece of information. They told me they're using 400 meters of fencing. Now, 400 meters of fencing doesn't really have anything to do with the area per se. 400 meters of fencing is going to go around, around, around. So that's going to talk about the perimeter of this particular shape. So I can then go and I can put up here, because we have 400 meters of fencing, I know the perimeter is going to be equal to 400. Now careful before you just use the normal formula for the perimeter of a rectangle, because normally you would go 2 times x plus 2 times y is then equal to the perimeter of 400. But not in this case. It's not going to be 2 times y because they used an existing boundary wall. So 2 times x, there we go, plus only 1y is then equal to 400. Now, this is the part that I said you need to go and substitute it in. So I was looking for something to substitute into that y, and this is what I'm going to substitute in. But obviously, I first need to put it in terms of y, so I can substitute y with whatever value it is with, well, not value, but whatever it is with regard to x. So I'm going to go and I'm going to substitute in there, y is equal to 400 minus x. And that's why they gave me this information about the fencing. So therefore, a is then equal to x times 400 minus x. And please be careful. Remember, we can't find the derivative of a product. So I first need to simplify using the distributive law, saying 400 times x and then x times negative x, which is minus x squared. So now I know that the formula for the area of this ostrich den, so this rectangular ostrich den, is then this. So now finally I can go back to this where it says to get a maximum or a minimum, set the derivative equal to 0. So we're going to be super lazy on our notation. I'm going to go, the first derivative of a is then equal to 400 minus 2x. I'm going to set that equal to 0. Remember, you have to show me that you're setting it equal to 0. If you just leave it open and then eventually you go and you solve the equation, they penalize you for that, because without the 0, it's not an equation. So 0 is then equal to 400 minus 2x, which means 2x is equal to 400. So that means x is equal to 200. Now please note, the question asks to calculate the dimensions for which the area is maximum. So we are saying when x is 200, so when the width is 200, we get a maximum area. But they didn't just ask for the width, they asked for both dimensions. So I now need to go and substitute this back in here. And I need to say y then will be equal to 400 minus 200, which means y is going to be equal to 200 as well. So this is actually a square if you think about it, because your width and your length are exactly the same. But please remember, people, a square is also a rectangle, so this is totally allowed. So with a width of x meters and a length of 200 meters, a width of 200 meters and a length of 200 meters, this will have a maximum area. Now please note, I haven't actually calculated the maximum area because they didn't ask for it. But if you do want to know what is this maximum area, you can simply go back to this, that one. So this right there is the formula that calculates my area. So please remember, if I want to know what that maximum area is, I can then go and say, so the maximum area happens when x is 200. So I can substitute 200 in there. So 400 times x, which is 200, minus 200 squared. So 400 times 200 minus 200 squared then gives me 40,000. So that means I will have a maximum area of 40,000 meters squared. Now again, they didn't actually ask this, but it's useful to know how to get to that maximum area. You just go and whatever dimensions you get over there, you substitute it back into the area formula, not into the derivative. That doesn't give me area, this one gives me area. So if I want to get the maximum area, substitute back in there. Good. Let's keep going on these examples. The next example is example 2 on page 228, and it tells me, a mining company manufactures rectangular storage containers from a rectangular metal plates. So you have a rectangular metal plate, which they've shown you over here. The rectangular metal plate measures 80 meters by 50 meters. So they told me the length of that plate is 80 meters and the width of that plate is 50 meters. Now what they do is they take these little squares, and these squares have side lengths of x, x, x. So these are congruent shapes, and all of them have that little side length of x. So they take these little squares and they cut it. So they cut out these squares from the corners. And they probably use it for scrap metal, but that's gone. So they cut that out, and these are congruent, each with a side length of x. They cut it out. Then they take and they fold on these dotted lines. So they fold that up, they fold that up, they fold that up, they fold that up, and then they form this container. Okay, so this rectangular container is then formed by folding these sides up after these little squares have been cut away. Now this is a nice example because they scaffolded. Unlike example 1, where you're supposed to just jump in, it's nicely scaffolded. So they start by saying, write down the length, the breadth, and the height of that container in terms of x. So we need to write the length, the breadth, and the height of that container in terms of x. So the first thing you need to know, obviously, the length used to be 80, but then I've cut these two squares out. So that x gets cut out. So that means the length is then going to be 80 minus 2x. Then the breadth of that particular container used to be 50. So we have 50, but they've cut this little side length of x, this little side length of x out. So that means the breadth is then 50 minus 2x. Now the height is then obviously, because I fold this up, this side length of x gets folded up. So the height over there is then just equal to x. So I've got the length, the breadth, and the height, all of that in terms of x. Now the B part of this question then says, derive a formula for the volume of the box in terms of x. Now the volume of that box is length times breadth times height. But they want it in terms of x, so we're just going to use these, I suppose it's a formula for length, breadth, and height. We're just going to use them in here to set up that volume in terms of x. So the length, we said, is going to be 80 minus 2x times the breadth, which is 50 minus 2x, times the height, which is then going to be x. Now, depending on whether they want it simplified or not, you might be able to leave it. Normally, they have to state and simplify. I am going to simplify it because since we are busy with optimization, I know we're going to have to find the derivative of this in the next step. And because we need to find the derivative of this in the next step, it's useful just to get rid of the products. Because remember, you cannot find the derivative of a product. You first have to simplify. Okay, so I'm going to leave the x first and multiply the binomial by the binomial. So if I look at 80 times 50, 80 times 50 is equal to 4,000. So this is going to be 4,000. That's going to be minus 160x. So minus 160, and this is going to be minus 100x. So minus 100x. So that's going to be minus 260x. And then this is going to be minus 2x times minus 2x, so that's going to be plus 4x squared. Now all of this still needs to be multiplied by x, so I need to distribute that x, which will then give me 4,000x minus 260x squared plus 4x cubed. There we go. Right, so this is then the formula for the volume in terms of x, and we're going to use that in the next step, because in the very next step they ask me, calculate the dimensions of the container for a maximum volume. Right, so calculate the dimensions of the container for a maximum volume. So that volume formula we've just established, I'm going to write it in descending order of powers, is 4x cubed minus 260x squared plus 4,000x. There we go. And like I said, whenever you see the word maximum or minimum, find the derivative and set it equal to 0. You don't even have to think about this. This is just something you need to know. So I'm going to find the derivative of that volume formula, which is then going to be 3 times 4, 12x squared, minus 2 times 260, which is going to be 520x, plus then 4,000. And that is what I'm going to set equal to 0, right over there. Now, especially in this case, because you don't really want to go and factorize and solve with these massive values over there. You could first check to see where the 12 divides into it, and maybe it'll be a little bit easier. But in all honesty, if you have a silver calculator, in this case, I would use it. So I would go and say mode, and we're going to set it up, equation mode, and we're going to go for number 3 because this one is a quadratic equation, so number 3. And I'm just going to, whoops, sorry about that. Let's try again, mode 5. There we go. So in this case, the A value is equal to 12. The B value is minus 520. And then the C value is going to be 4,000. Which means they give me my 2x answers. They say the first answer for x is equal to 100 over 3. Or they go x is equal to 10. Now, if you get 2 answers, then this means I've got a little bit of a problem. And the reason I've got a little bit of a problem is one of those answers is probably the maximum volume, the one that gives me the maximum volume, and one of those is probably the one that gives me a minimum value. Now I'm just going to go and I'm going to take that 100 over 3 and I'm going to change that. Sorry, let me just do this. I'm going to change that into a decimal place, 1 decimal place. So I'm going to change to 33,3. Good. Now, if you want to know which one of those is the maximum or the minimum, you have a couple of options. The first option is you can find the second derivative, because remember, we have a second derivative test to establish minimum and maximum. So that's not a bad option. You can go and you can say second derivative is then going to be from here 24x minus 520. And you can then quickly just substitute these values in there to see which one of them gives you a minimum and which one of them gives you a maximum. So to do that, I'm just quickly going to go and say, let's first substitute 33,3 into the second derivative. So I'm going to go 24 times 33,3 or 100 over 3. I suppose 100 over 3 is more accurate, so I'm going to use the 100 over 3 minus 520. So this gives me a positive value, that second derivative. So that one, if I sub it in, gives me a positive value. Now this one, if I sub it in, let's see what it does. So I'm going to go 24 times 10 minus 520 is then equal to a negative value. So I've just gone and I've substituted those x values into the second derivative. So obviously, if the second derivative is positive, it's concave up. If the second derivative is negative, it means it's concave down. And because that second derivative is negative and it's concave down, this is the maximum, whereas this one is the minimum. So that means specifically here, 10, that one right there, that's the one that gives us a maximum. This one gives us a minimum, and they ask for a maximum volume, so I'm going to continue with x equal to 10. So the question was, calculate the dimensions of the container for a maximum volume. So the dimensions we stated over here, right over there. Length is equal to 80 minus 2x. So let's put it side by side, see if it fits. Maybe if I do this. So length is then equal to 80 minus 2 times 10. Because we said where x is 10, I get that maximum value. Then my breadth is going to be equal to 50 minus 2 times 10. And then my height, there we go, is then just going to be equal to 10. Now if I calculate that, that's 80 minus 20 is 60 meters. And then my breadth 50 minus 20 is going to be 30 meters. So for those dimensions, let me just move up. Sorry about that. There's the height, 10 meters. So for those dimensions, I then end up having a maximum volume. Again, I haven't actually calculated the maximum volume. I can actually calculate it by simply going and substituting this back into that one, if they ask for it. So because I know at 10, x equal to 10, I have a maximum volume, if they ask for that maximum volume, you can then go and you can substitute it back into that original equation to give it to you. But in this case, they didn't ask for it, so I'm just going to leave it right there. Now, the last little example we need to look at in this particular lesson is something completely different. The first two dealt with perimeter, area, and volume, which is a very common question in past paper examples. This one I have seen before in past paper examples, and specifically it refers to the length of a line segment. So example 3, page 229. The graphs shown are defined by the equation. So the first graph is defined by the equation 2y plus x minus 12 is 0, which is a straight line equation. So I'm just going to put it in standard form, where 2y is equal to minus x plus 12, and then dividing by 2, y is equal to minus x over 2 plus 6. There we go. So that's the equation of that straight line. And then they've defined the second one, the hyperbola over there, as xy is equal to 2. So again, people, I know that's a little bit strange. So I'm going to just go and I'm going to change that to y is equal to 2 over x. And then hopefully you will see that is the equation of a hyperbola. Then they've also stated PQ is perpendicular to the x-axis. So if you extend PQ over there, they've told me it's perpendicular to the x-axis, which means it's a vertical line. With P on the straight line, so P is a point on the straight line, and Q is a point on the hyperbola. So this is the length between two graphs. Now hopefully you guys will remember that if I want to get the length between two graphs, or the distance between two graphs, in this case PQ, I need to go and say it's the top graph, which is that, so minus x over 2 plus 6, minus the bottom graph, which is that, so minus 2 over x. That's how I managed to find the length of PQ. I can also just call it the distance. And I'll show you just now why I called it the distance. But the distance between the two graphs, in this case PQ, is going to be the equation of that straight line minus the equation of that hyperbola. Now what's the question? The question they ask is they ask for a maximum, so they're asking me for a maximum length of PQ. So that means I'm trying to optimize this. And the good news is it's already set up. I will just have to change one or two things to make it easier to find the derivative, but it's already set up as an equation for maximum length. So I'm going to call it just the distance between the two graphs, and that I'm going to change to minus a half x plus 6, and then I'm going to take this to minus 2x to the power of negative 1, because remember you can't find the derivative if x is in my denominator. So again, why are we looking at the derivative? Because I'm looking at maximum and minimum. And whenever I look at maximum and minimum, it's where the derivative is equal to 0. So first things first, I'm going to find that derivative, and that's going to be minus a half. Derivative of a constant is 0, and then negative 1 times negative 2 is plus 2x to the power of negative 2. I'm going to set the derivative equal to 0. So I have that minus a half plus 2 over x to the power of 2. And again, we did say try and change those negative exponents to positive exponents. Why? It's a good habit, and especially it helps when you're solving equations. So now in order to solve this equation, we need to find the LCM of the denominator, which is going to be equal to 2x squared. Now, I'm going to consider that minus to be above the line. That's why I didn't say the LCM is negative 2x squared. I'm just going to use that 2x squared. Right, so I multiply and I get 0 is equal to, now 2 divides away, but that means the minus 1 still needs to be multiplied by x squared, so it's minus x squared. And then over there, the x squareds divide away, so I still need to get that 4, because 2 times 2 is 4. So I'm going to transpose this, and I'm going to say x squared is equal to 4. And careful with this, people. Be very, very careful. The moment I draw that square root, I need to put the plus minus, because it's a quadratic equation, and a quadratic equation normally has two answers. So x is then equal to plus or minus 2. Now, they did say right at the beginning, if you read through the example in your textbook, they did go over here and they said that x is greater than 0. So they did go and say the x is greater than 0. So because the x value is greater than 0, then logically speaking, I'm not going to use the negative 2. I'm then going to go and say x is equal to positive 2. Now be careful, because we haven't answered the question. They didn't ask for which x value do I have a maximum length. They asked what is the maximum length. So I now know at x equal to 2 I've got a maximum length. But in order to find that maximum length, I need to substitute it back into the equation that gives me the maximum length. Or I can even substitute it back into this equation that gives me the maximum length. I'm actually going to use this one. So I'm going to say the maximum length of that PQ is then equal to minus x over 2. So minus 2 over 2 plus 6 minus 2 over 2. There we go. So that's going to be minus 1, which is minus 2, plus 6, which is 4. So the maximum length of PQ is then equal to 4 units, and that happens where x is equal to 2. So these are the examples. Like I said, I haven't used the Luzandi method. I haven't gone step by step by step. I will do that in the next video. I just wanted to go through a couple of ideas on how to look at these, because if I just go and I start with the steps, you guys are going to have no clue as to what I'm talking about. So in the next video, I will talk about the steps and then I'll do some past paper examples. Thank you for listening.